Hello everyone, this is Shalini here. Welcome to my channel Higher Mathematics with Shalini. In this video, I will see metric topology and proof. Right students? So what is the metric topology? The definition of metric topology is let Xd be a metric space, let Td consist of phi and all those subsets G of X having the property that for each X belongs to G, their exist R is greater than 0 such that Sx are contained in G. Then Td is a topology on X called metric topology induced by metric D. Right students? What is the Td? Td is the collection which contains phi and all those subsets G of X. Td contains all those subsets of subset G of X having the property that for each X belongs to G, their exist R is greater than 0 such that Sx are contained in G. What is a Sxr? Sxr is an open sphere with center X and radius R. Here X is the center and R represent radius of an open sphere. Right students? Then TED is a topology on X called metric topology induced by metric D. Okay students, metric topology is same as usual topology. The difference between metric topology and usual topology is that in usual topology, here we need to understand we take for every X belongs to X, there exists X plus epsilon open interval X minus epsilon X plus epsilon contained in G. Right students? In usual topology, for every X belongs to X, there exists epsilon is greater than 0 such that we get an open interval such that which contained in G. But in metric topology, for every X belongs to G, there exists R is greater than 0 such that we get an open sphere Sxr contained in G. Right students? Now some students may have a doubt. What is the doubt? Here why we are consider open sphere, why we are not consider open interval X minus epsilon X plus epsilon. So students, in usual topology we are studying on real line, right? The collection T is a topology on R, right, in usual topology. And in metric topology we study in space. Xd is a metric space, right? So here we get an open sphere with center X and radius R. I hope you are getting my point. Now we shall prove this. Td is a topology on X, right? So let Xd be any metric space. What we consider? Let Xd be any metric space and Td is equal to G. The collection Td, G is subset of X such that G is equal to phi union of X belongs to G, there exists R is greater than 0 such that an open sphere Sxr contained in G, right? Td contains phi and those subsets of X which X belongs to G, there exists R is greater than 0 such that Sxr contained in G. We shall prove Td is a topology on X. So what is the condition of topology? The first condition is phi belongs to T, right? And so phi belongs to T. From here Td consists of phi. T contains phi already, right, by definition. So phi belongs to T by definition. Now we shall prove that R belongs to Td, right? Sorry, here Td, not T, right? So for any X belongs to X and for any real number R is greater than 0 such that Sx are contained in X, right? Students, X is a universal set. We take and Td, what is Td? Td is G subset of X such that G is equal to phi union X belongs to G and G is a subset of X. So if X belongs to G, then small x also belongs to capital X, right? So we consider for any X belongs to X and for any real number R is greater than 0, what is R? R is a radius, right? And distance is always positive, so R is always positive. It is non-negative, right? So R is greater than 0 such that Sxr, open sphere Sxr contained in X, right? By graphical method we need to understand. Suppose suppose X is a universal set, right? X is a universal set. Suppose I take a point X, right? You take this point anywhere inside X, right? Here you can take here, 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 anywhere, right? So suppose I take a point X in here, right? So we can draw an open sphere with center X and radius, positive radius R. We can draw an open sphere like this, right? Here also, if here I take a point X, then also we can draw an open sphere with center X and radius R. This is the R. This is the radius R, right? So we can also draw here, we can also draw here, right? So, and students, R is positive but not so large. R is a small radius. Suppose I take a large radius like this, right? Suppose here a point X and radius large, little bit large, then we can draw an open sphere with center X and radius R like this, right? If I take radius so large, then what is the problem? The problem is our open sphere not properly contained in X, right? So, that is why I am taking always a small radius, not so large. This is the reason. I hope you are getting my point, right? So this implies that X belongs to TD. Why? Because X satisfied this condition. Second condition, what is the second condition of topology? Second condition of topology is if G1 belongs to T and G2 belongs to T, implies that G1 intersection G2 belongs to T, right? So suppose let G1 belongs to TD and G2 belongs to TD, right? Okay. Now suppose let G1 belongs to TD and G2 belongs to TD. Let X belongs to G1 intersection G2 be an arbitrary point, right? Suppose let G1 belongs to TD and G2 belongs to TD. Let X belongs to G1 intersection G2 be an arbitrary point. Here second condition is let G1 belongs to TD and G2 belongs to TD. Then what we will show that we shall show that G1 intersection G2 also belongs to TD. So here some students may have a doubt. What is the doubt? Doubt is if G1 intersection G2 are disjoint, right? If intersection of G1 and G2 is equal to phi. So students, if I take G1 intersection G2 are disjoint, that means if G1 intersection G2 is equal to phi, then phi is also belongs to TD. That is why I am not consider phi, right? So I consider G1 intersection G2 is not equal to phi. If G1 intersection G2 is not equal to phi, that means let at least one point in intersection of G1 and G2, right, be an arbitrary point. If X belongs to G1 intersection G2, this implies that X belongs to G1 and X belongs to G2, right? If a point and X belongs to G2, right? If X belongs to G1 and X belongs to G2, what we can say? 1 and G1 belongs to TD, X belongs to G1 and G1 belongs to TD. This implies that there exists X1 is greater than 0 such that SXR1 contained in G1, right? Here G1 belongs to TD. If G1 belongs to TD, that means G1 satisfied this condition. G1 satisfied this condition, right? So there exists X1 is greater than 0 such that SXR1, here R1, right? There exists R1 radius R1 is greater than 0 such that SXR1 contained in G1, right? Similarly, X also belongs to G2, right? If X belongs to G2 and G2 belongs to TD, G2 is also belongs to TD. This implies that there exists R2 is greater than 0 such that SXR2 contained in G2. X belongs to G2, and G2 belongs to TD. This implies that there exists R2 is greater than 0 such that SXR2 contained in G2, right? Now we shall prove that now for proof this, now our aim is to show that for X belongs to G1 intersection G2, there exists R is greater than 0 such that SXR contained in G1 intersection G2, right? For proof this, our aim is to show that for X belongs to G1 intersection G2, there exists R is greater than 0 such that S an open sphere SXR contained in G1 intersection G2. If we have shown that this condition, then G1 intersection G2 belongs to TD, right? If we have shown this condition, then my work is done. G1 intersection G2 must belongs to TD, right? Then let R is equal to minimum of R1 R2, right? Similarly, we have already told in usual topology why we are taking minimum of epsilon 1 epsilon 2. Here radius, here R1 R2 is radius, so why we are taking minimum of R1 and R2? So here we need to understand. Suppose I take a universal set X, right? Here we take a point X. Suppose we draw an open sphere with radius R1 like this, right? Suppose we draw an open sphere with radius, this is the R1 and this is the R2, right? This is the G1 open sphere and this is the G2 open sphere. Suppose here we take a point X, we draw an open sphere with radius R1 and we draw another open sphere with a center X and radius R2, right? Here R1 is smallest and R2 is largest, right? Here R1 is smallest and R2 is greatest. G1 is this, G2 is this. Now here why we are taking minimum of R1 and R2? So students, we are taking minimum of R1 and R2 because suppose I take R is equal to maximum of R1 and R2, then what will be happen? Here suppose I take R is equal to maximum of R1 and R2, right? Here largest radius R2 is this is an open sphere of largest radius R2, right? And this is an open sphere of radius R1, smallest radius R1, right? So from here we can say that if we are taking R is equal to maximum of R1 and R2, then what can we say? We can say that SXR contained in SXR2, right? Here the largest radius R2 and R2, if R2 is maximum, then SXR what is the R is maximum of R1 and R2. If maximum of R1 and R2, then SXR contained in SXR2, right? Why? Because R2 is maximum. And but SXR does not contained in SXR1, right? Here SXR contained in SXR2. Why? Because R2 is largest radius, right? Here R2 is maximum from R1. And here what we take? We take R is equal to maximum of R1 and R2. But here if I take maximum of R1 and R2, this implies that SXR contained in SXR2, but SXR does not contained in SXR1, right? Why? Because R1 is smallest open sphere with smallest radius R1, right? Because G1 is smallest open sphere with radius R1. So that is why we are taking always R is equal to minimum of R1 and R2. not maximum, right? If I take maximum, then SXR does not contain in SXR1, right? And if I take minimum, then if I take, suppose, now let what R is equal to minimum of R1, R2. If I take minimum, then what can we say? We can say that SXR contained in SXR1, SXR contained in SXR2, right? Here both conditions are satisfied. Here we get an open sphere SXR which contained in SXR1 and which contained in SXR2 also, right? So now students, I hope you are getting my point, why we are taking minimum of R1 and R2, why we are not taking maximum of R1 and R2, right? Here, from here, right? So students, if I take R is equal to minimum of R1, R2, what can we say? We can say that SXR contained in SXR1 contained in G1 S. This implies that SXR contained in G1 intersection G2, right students? And what we have shown? We have shown X belongs to G1 intersection G2, there exists R is greater than 0 such that SXR contained in G1 intersection G2. We have already shown SXR contained in G1 intersection G2 for X belongs to G1 intersection G2. Here, from here, X belongs to G1 intersection G2, we have already shown and there exists R is greater than 0 such that SXR contained in G1 intersection G2, right? So we write, we have shown that for X belongs to G1 intersection G2, there exists R is greater than 0 such that SXR contained in G1 intersection G2. This implies that G1 intersection G2 must belongs to TD, right students? If G1 belongs to TD and G2 belongs to TD, this implies that G1 intersection G2 also belongs to TD. This implies that second condition is satisfied. Third, let G lambda belongs to TD, right? What we consider? We consider G lambda belongs to TD for all lambda belongs to capital lambda, where capital lambda, what is capital lambda? Capital lambda is index set. It can be infinite, it can be finite. Let X belongs to union of G lambda. Lambda belongs to capital lambda. Then students, here we consider G lambda belongs to TD for all lambda belongs to capital lambda. Let X belongs to G union of G lambda. Lambda belongs to capital lambda. What we consider? Here we consider X belongs to union of G lambda. Okay? Union of G lambdas means X belongs to G1 or X belongs to G2 or X belongs to G3 and so on, right? If X belongs to any G lambdas, then X belongs to union of G lambdas, right? So here X maybe belongs to G1, X maybe belongs to G2 and X maybe belongs to G3. So we can say that X belongs to union of G lambdas, right? So here we consider X belongs to union of G lambdas, lambdas belongs to index set, such that then here let X belongs to union of G lambdas, lambdas belongs to index set, then there exists lambda belongs to capital lambda, lambda naught. Here lambda naught, suppose here there exists a lambda naught belongs to capital lambda such that X belongs to G lambda naught. Students, here suppose X belongs to G1, here suppose lambda is equal to 1, 2 and so suppose X belongs to G2, here lambda naught is equal to 2. Similarly, here there exists lambda naught belongs to capital lambda such that X belongs to G lambda naught. If X belongs to G lambda naught, then also X belongs to union of G lambdas, right? As X belongs to G lambda naught, and as x belongs to G lambda naught, here x belongs to G lambda naught and G lambda naught belongs to TD, right? Here G lambda belongs to TD, for all lambda belongs to capital lambda, and G lambda naught also members of capital lambda. So G lambda naught also belongs to TD. If G lambda naught belongs to TD, what can we say? We can say that this implies that there exists R is greater than 0 such that Sx are contained in G lambda naught, right? Why? Because G lambda naught belongs to TD. If G lambda belongs to TD, then what is the definition of TD? Definition of TD is G subset of X such that G is equal to phi union of X belongs to G. There exists R is greater than 0 such that Sx are contained in G, right? So if G lambda naught belongs to TD, then this satisfied this condition, right? If this satisfied this condition, as G lambda naught is contained in union of lambda belongs to capital lambda, G lambda, this implies that Sx are contained in union of lambda belongs to capital lambda, G lambda, implies that union of lambda belongs to capital lambda, G lambda belongs to TD, right students? From here we can say that implies that union of lambda belongs to capital lambda, G lambda belongs to TD. Hence TD is a topology on X. I hope students this video is helpful for you. Still you have any doubt related to this topic, please let me know in the comment box below. I will try to clear your all doubts. So till then, bye bye, take care. Thanks for watching.